What if the software that routes calls for entire countries could heal itself faster than it could fail, trade single-thread speed for orchestration strength, and evolve while staying online? Legacy telecom stacks promised stability and delivered outages. Monolithic processes swallowed faults whole. Upgrades meant maintenance windows that stretched into mornings. The cost was measured in dropped calls, angry regulators, and lost revenue. The question in Stockholm was simple and cold. What would it take to make failure boring? The pain was not abstract. Carrier networks in the late 1980s through the early 2000s ran on strict service-level promises that punished downtime. Multi-hour outages cost millions. Switches were expected to hit 5 nines availability. That means minutes of downtime per year, not hours. Nodes had to patch and roll forward without dropping live calls. Control planes juggled millions of concurrent sessions, while the data plane pushed bits with no patience for stalls. Every upgrade was surgery on a beating heart. Every pager alert carried the same subtext. Do not let the network fall off the air. The protagonists were 3 engineers at Ericsson in Stockholm: Joe Armstrong, Robert Virding, and Mike Williams. They worked in the shadow of the great switching programs and within sight of ideas coming from Bell Labs about processes, message passing, and fault containment. Their world was telephony, not websites. Their constraints were line cards, trunks, and exchanges. They were asked to build software that would not flinch when a single module misbehaved, that could replace parts in flight, and that would scale horizontally without teaching every developer to become a lock whisperer. They chose a design philosophy that put fault tolerance ahead of raw speed. They wrote a language where the default is isolation, where a process can crash without bringing down its neighbors, and where supervision trees restart the broken parts in known states. Distribution is not an afterthought, but a first principle. Nodes talk in messages. No shared memory. No locks across the boundary. As Joe Armstrong liked to say in one of his many formulations, reliability follows from isolation. Keep things separate, let them fail safely, and recover under watch. The world is concurrent. Things fail. Structure the system so that failure is local and recovery is automatic. They built on the Beam virtual machine. Instead of heavyweight threads, Beam runs millions of lightweight processes scheduled preemptively across cores. Each process owns its heap. That means garbage collection happens per process, in tiny pauses that do not block the world. Each process has a mailbox. Messages are copied in, pattern matched, and handled in order. Hot code loading lets a module be upgraded live while existing processes continue, then tail into the new version when they touch it. OTP provided the scaffolding. Behaviors like gen, server, and supervisor made the architecture repeatable. A crash is contained by design. A supervisor notices and restarts the child with a clean state. If the fault persists, the supervision strategy escalates. If a node fails, distribution protocols move traffic to healthy peers. The goal is simple. Faults should be events, not incidents. The milestones trace a line from lab to backbone. Erlang took shape internally at Ericsson in the late 1980s and early 1990s. The AXD 301 ATM switch, shipped at the turn of the millennium, became a flagship of the approach, running millions of lines of Erlang with operational metrics that matched the 5 nines brief. In 1998, Ericsson open-sourced Erlang and OTP. The internet era caught up in the 2000s and the 2010s. RabbitMQ brought robust messaging to web companies. CouchDB embraced the same model for a distributed document store. React carried the torch for eventually consistent storage. WhatsApp ran a tiny operations team against global-scale concurrency using Erlang. In the early 2020s, OTP24 introduced a JIT compiler for Beam, sharpening latency and throughput without giving up the per-process guarantees. The head-to-head comparisons are revealing. C and C++ dominate for bare metal performance and bespoke threading. They are unmatched for tight loops, specialized memory layouts, and instruction-level control. But they make you carry every concurrency decision by hand. One forgotten lock and the pager rings. Erlang trades single-thread peak for rapid failover. When a process dies, supervision recovers it in milliseconds. If the priority is never dropping control messages and recovering cleanly, Erlang has the edge. If the priority is squeezing every cycle from a codec or a SIMD filter, C or C++ still win. Java on the JVM brings massive enterprise tooling and high throughput. The runtime has decades of performance work, mature observability, and armies of developers. But the garbage collector is usually global in spirit, even when concurrent, and the supervision model lives in frameworks rather than the language's bones. Erlang's soft real-time schedulers and per-process garbage collection keep tail latency predictable under bursty load. Java's throughput can be higher in homogeneous workloads, while Erlang's operational complexity under failure is lower because the restart story is standardized and pervasive. Go ships static binaries and a simple model inspired by CSP. Go routines are easy to create, channels are approachable, the standard library is strong. In many service backends, Go delivers excellent throughput with straightforward deployments. Erlang differs in 3 important ways. Schedulers are preemptive at the language runtime level. Garbage collection is per process, so pause times are short and isolated. Distribution and supervision are first class, not patterns layered on top. Teams pick Go when they want single binary deployment ease, strong dev familiarity, and solid performance for straightforward network services. Teams pick Erlang when tail latency, transparent distribution, and fast crash recovery under chaotic traffic matter more than single-thread speed. There are downsides and failure modes. Numerical and CPU-bound workloads underperform compared with C or Go. Native implemented functions, the bridge to native code, can hurt scheduler responsiveness if they block for too long. The ecosystem has gaps for data science and desktop user interfaces. The hiring pool is smaller. The syntax is unfamiliar to many developers and slows onboarding. At very high data rates, distribution, overhead, and message copying costs show up. Cross-node net splits can create subtle behaviors if global registries or cluster-wide locks are misdesigned. Real systems adapt. A common pattern is to keep orchestration in Erlang or Elixir and move hot loops to native code or to a sidecar service. The Discord team, running on the Beam via Elixir, wrote critical codecs and compression paths in Rust as NIFs and services while preserving supervision and orchestration on the VM. The lesson is not that Beam failed. It is that isolation at the system level makes hybrid architectures practical. Erlang's strengths remain at process supervision, failure containment, and live upgrades. The compute-heavy parts live where hardware vectors and static compilation pay off. The impact at scale is measured in operator sleep. 5.9's ambitions move from slide decks to dashboards. Rolling upgrades with near zero downtime are standard practice rather than heroic acts. Millions of lightweight processes run on commodity hardware without turning tail latency into a lottery. Pager fatigue goes down because restarts are local and scripted. Mean time to recovery shrinks because supervisors act in sub-second windows and logs point to failing children, not entire monoliths. When something new is deployed, the system evolves live. The beating heart keeps its rhythm. Today, the Beam sits under a quiet list of familiar names. WhatsApp kept an extremely small operations headcount while serving global messaging. RabbitMQ remains a backbone of durable message queues across industries. CouchDB and the React lineage showed how to push consistency choices to the edge and keep clusters stable. Klarna built fintech services on top of OTP behaviors. Bet365 used Erlang in parts of its betting infrastructure where bursty traffic meets hard uptime promises. Elixir rides the same VM, opening the door to teams that prefer its syntax and meta-programming. In the near future, the themes are clear. Schedulers and the JIT will keep improving. Distribution, visibility, and tooling will tighten, making cross-node issues easier to diagnose. Safer native interfaces will reduce the risk of blocking schedulers. Observability will grow closer to the supervision tree model, turning failure charts into maps. There are times when Erlang is not the right choice. Heavy numerical computing, GPU workloads, and most machine learning research stacks sit better in Rust or C++ for tight loops, or in Python and Julia ecosystems for libraries and tooling. For simple network services with strong operations familiarity and off-the-shelf observability, Go remains a solid option. If your team needs desktop interfaces or data science notebooks, the Erlang ecosystem will not help much. Pick it when your system must evolve live, keep tail latencies tight under stress, and survive faults as a matter of routine. The closing thesis is not romantic. Erlang traded peak single-thread speed for system-level reliability, isolation, and live evolution. It forced the idea that software should fail under guardrails and come back as a matter of course. That bet pays off wherever downtime is unacceptable and where recovery matters more than denial. In a world that only grows more concurrent, that choice still looks like the right one.